Welcome everyone to Wednesday Night The Lab. I'm Tom Zinnan. I work here at the UW-Madison Biotechnology Center. I also work for the Division of Extension here. And on behalf of those folks and our other co-organizers, Wisconsin Public Television, the Wisconsin Alumni Association, and the UW-Madison Science Alliance, thanks again for coming to Wednesday Night at The Lab. We do this every Wednesday night, 50 times a year. Tonight, it's my pleasure to welcome Daniel Wright of the Department of Civil and Environmental Engineering here. This is a night of perfect weather, and the irony is we have perfect weather to talk about what's up with all these storms and floods. Daniel was born in Ann Arbor, Michigan, and went to high school in Chelsea, Michigan. And then he went to the University of Michigan and studied civil and environmental engineering. Then he went to the Peace Corps for 2 years in Bolivia. And then he came back to the U.S. and went to Princeton University and got his PhD in civil and environmental engineering. Then he did a postdoc at the Goddard Space Flight Center near Washington, D.C. In January 2016, he came here to UW-Madison. I want to point out that in 2018, he won a National Science Foundation career grant. I think they give away maybe 30 of those a year across the country. That was one of the events that I got the right to speeches for the director of the National Science Foundation. So anytime I introduce somebody that got a career grant, it's like, whoa, that's pretty impressive. So please join me in welcoming Daniel Wright to talk about what's up with all these storms and floods here at Wednesday Night at the Lab.
Okay, I'm also very appreciative of everybody coming out tonight. It's great to see an almost full room. And yes, indeed, we are going to talk about what's up with all these storms and floods. I was asked to, try to throw a little bit of my own journey as a scientist into this talk, so I'll try to do that a little bit up front and by sharing, one little piece. You heard that I was a postdoctoral research fellow at Goddard Space Flight Center. That's one of NASA's research and development campuses. It's just on the road towards Baltimore, just north of Washington, D.C. And so I was living in Washington, D.C. at the time. And have any of you spent any significant time in Washington, D.C. in the past? Yeah, so a fair number of you. So you know the thing that happens in D.C. when you meet somebody for the first time, they immediately ask you what you do. And so I think probably because they want something from you, or they're trying to figure out if they can get something from you. So anyways, I would tell them that I work at NASA and I work on floods. And then they get a real confused look on their face, and they come back with, so floods on Mars? Which, is not such a crazy question, really, when you look at an image like this. So that's an artist's rendition of the surface of Mars, and it does actually look from that image that floods did happen there at some point in time. We're going to keep things squarely on planet Earth this evening, and so I'll tell you why I was spending time at NASA. So this video here is showing what we call the constellation of satellites that are part of the Global Precipitation Measurement Mission. And so some of these are from NASA, some of them are from NOAA, and some are from other space agencies around the world. And together, over the course of a day or so, they can end up filling in a nice picture of what precipitation over the entire globe might look like. And so after taking the satellite images from all of these different satellites and stitching them together, you can get some nice images like this, which is 1 day's worth of precipitation over the entire globe. And this has a ton of useful purposes, both in climate science, weather science, and with what I do, which is trying to understand floods and other hydrologic extremes. So I'm not going to say much more about the satellite side of things, but it is a big part of what we do. And so this is the Hydroclimate Extremes Research Group at UW-Madison, and actually most of them are sitting there in the back. Why don't you guys raise your hands? They're the ones that end up doing most of the work, and I get most of the glory. So what is it that we do? So I alluded to this on the previous slide, but we look a lot at rainfall and flood measurements and try to understand how accurate they are. And if that doesn't sound very interesting to you, that's perfectly reasonable. We're not going to talk about that tonight. What we're going to focus on instead is using statistics and computer simulations to study the role of rainfall and other factors mainly in floods, but we also have a big project with NASA on landslides as well. And then as engineers, we also work on this last part, which is developing software, both for our own research, but also to help other people answer their own sorts of questions. And so, I'm an engineer by training, or I guess also a hydrologist by training, but we end up doing a little bit of all of these different things and interacting with people from all of those different fields. And so that's really one of the nice things about this line of work, is that it does bring us into contact with a lot of different folks and a lot of different ideas. Okay, so let's start talking about floods. And so this is a picture from August of last year in East Madison. And just to remind us, I suppose that most of you were around for this, but we had really, really heavy rainfall, upwards of 15 inches in some isolated pockets, falling over the course of about 6 hours, and that caused, particularly in West Madison and farther west, localized flash flooding. And then as that water made its way into the chain of lakes, we had some issues with backing up storm sewers and things of that nature. So, so that's one sort of flavor of flooding that you could imagine. This is another one. So this is a picture that I took at the end of May of this year as we were about to land in Omaha, Nebraska. So if I'm not mistaken, where's my cursor here? There it is. So this is the Missouri River back here, I think. Hopefully no one from Omaha can prove me wrong. I should have looked at a map ahead of time, but I think that's right. And, so you see the interstate is fortunately not underwater, but some of these other arterial roads are. And, sort of the scale of this picture is much bigger than the one on the previous slide, right? And so what happened here, and probably many of you are familiar with this, but basically we had a cold winter, we had a lot of snow, we had a cold spring, that snow stuck around for a long time, and then the rain started. And so you had that combination of maybe not quite as intense rainfall, but lasting over long time periods, falling on snow, melting it, and this whole mess of things going downstream. And so the big difference here is not only the scale, so this was all over the Midwest, right, but also the time scale. So taking, instead of hours to set up, like in Madison, taking weeks or even months to set up. So this just gets to the point that there are some very different sorts of combinations of processes that can happen to create floods. So this is earlier this week in Washington, D.C. Again, another example of one of these very brief rainstorms that just dumps a lot of rain and creates all sorts of problems. I'll come back to that photo in a second. And then this is from this morning in New Orleans. My understanding is that this situation that was bad in the morning is getting worse by the minute and is not likely to let up anytime in the next couple of days. So that's going to be an interesting one to keep an eye out for. And in this case, a totally separate set of circumstances where you have a developing tropical cyclone that wasn't present in any of those other previous examples. Okay, so what's up with all these storms and floods? Well, this is the outline of what we're going to visit tonight. We'll start with talking a little bit about what we know. particularly about flood impacts, and I'll say what I mean by that later on, and then also about increases in temperature and rainfall. From there, talk a bit about how floods occur and why, well, and really, are they changing in a warming climate? The answer is a little bit complicated. And then look at two examples of the link between climate change and floods that in particular use computer simulations for them, which is a big part of what we end up doing. Then we'll wrap up with a quick summary and have plenty of time for the Q&A session, which I think is probably the most important part here. So please be thinking of things that you would like to talk about when we reach the end of my presentation. Okay, so floods, as the slide says, they're the most common natural disaster worldwide. They're amongst the most impactful. So here we can see the total number of federal flood declarations since 1963. If you do the math on this, that works out to about 1 per day over that time period. And so, from some perspective, then these are sort of an everyday occurrence, even if we might not think of them that way in our own lives. And then the other thing that you'll notice is that the Midwest is at least as badly affected by these things as anywhere else in the country. One thing that I forgot to mention in my bio is that I did a short stint at the World Bank before going to NASA, and so we were working on disaster risk management issues in Latin America and the Caribbean, and as part of that I put together this map. And so each of those dots is a reported flood. The dot size is in accordance with the number of people who were displaced from their homes. And then we highlight a couple of particular flood events there. So, you see some pretty shocking numbers, right? So Hurricane Mitch, for example, killing 15,000 people. La Tragedia de Vargas in Venezuela, killing 20,000 people. And then floods displacing upwards of 1 million people or more. So, really dramatic impacts. And the same is true in other parts of the world as well. Okay, so what do I mean when I say impacts? What I want to do is draw the distinction here between impacts and floods themselves. So I am a flood researcher, but what I do is really focus on the physical phenomena of floods, how they happen, how often they happen, how they might be changing. But that there are other types of flood researchers that focus on different things. So, for example, the economic impacts, the public health impacts, fatalities, mental health impacts, etc. And so I'm going to just review briefly kind of what we know about the impact side of things, and then we'll get into more of the physical phenomena, which is my specialty. So when it comes to flood fatalities, there's a lot of good news here, both in the U.S. and elsewhere. So we see basically no increase in flood fatalities since 1940, despite our population going up by roughly 2.5 times. And that's largely due to better weather forecasting and better flash flood communication. And that holds up in other parts of the world as well. On the other hand, if you look at economic impacts, so here you can just pay attention to the blue line. And this is global impacts, but this is true perhaps even more so in the US specifically. But these economic impacts are going up and up and up. And climate change could have something to do with this, but really the main driver by far is just the fact that our economies have grown substantially over that time period, and a lot of that growth has occurred in flood-prone areas. Another interesting point here, when you look at flood fatalities, basically getting killed in flood is a guy thing. So it's not coincidence here, that this is the kind of, that these two gentlemen are in the situation they're in, and you don't see any women standing on top of their cars. So, the basic story is, if there's going to be a flood, just stay home. And then when it comes to managing the impacts of floods, there's also good potentially good news if decision makers are willing to act on it in any way. So this is a figure that I took from a World Bank report where they basically were looking at the benefit-cost ratios of different types of investments or different types of projects that the World Bank likes to get involved with. And what you see is that both early warning systems and these measures to reduce damage from, long-term measures to reduce damage from floods are among the most cost-effective types of projects that they deal in. And so there can be a lot of bang for your buck when it comes to dealing with these sorts of problems. Okay, so now I'm going to shift gears into talking about floods as more of a physical phenomena. But I'm going to start talking about temperature. And the reason for that is really shown in this graph. So this is what we call the Clausius-Clapeyron equation in graphical form, I suppose. And so we have a number of different substances here that are liquids at room temperatures, including water. And the basic story is as the temperature goes up, the vapor pressure of these liquids goes up, specifically the saturation vapor pressure goes up, which in layman's terms just means that these liquids will more readily evaporate into the air. And so you, as long as that liquid is present, you're going to have more of that of vapor in the air. And so, that's of course important then when we're talking about heavy rainfall, because temperatures both regionally and beyond are going up. And so we see certainly increases in recent decades in temperatures in the upper Midwest. But it's a little bit more complicated story than this. And, this is really where the research is heading these days. And we need to look beyond just the regional map to bigger maps of the country and even beyond the country itself. Because if you think about the heavy rainfall that falls here in Wisconsin, most of that is actually coming from the Gulf of Mexico. And so you might need to worry perhaps even more so about the kinds of temperature changes that are taking place there than what's happening here. Okay, so we have regional and national perspectives that are important, but we also have local perspectives that are important, and I'm going to give what I think is an interesting example of this much later on in the talk, but I think we can all relate to the fact that urban areas can get quite hot. Basically, your pavement, your buildings, etc., can absorb and hold heat much more readily than natural surfaces, and this we call the urban heat island effect, and so the result is just higher temperatures in urban areas compared to their surroundings. Okay, so that's the sort of temperature side of things, and as I said, that's going to feed into increasing precipitation. This is annual precipitation in Wisconsin, so here we're not necessarily talking about those extreme rainstorms, but rather on a yearly basis what's happening, and that annual rainfall is going up. And it's likely to continue going up. And in fact, here you see an article from Weather Underground where they said the last 12 months have been the wettest 12 consecutive months in U.S. history. Okay, so that's the sort of annual perspective. This is more on the perspective of extremes. So this is a paper that actually was accepted to Geophysical Research Letters 2 days ago. And I just got contacted this morning saying they want to do a press release, so this might actually be coming out to a newspaper near you. We'll see how it goes. But here we're looking at storms that are larger than the 10-year storm or larger than the 100-year storm. And so we don't need to worry about this too much, but basically 10-year storm, it's got a 1 in 10 chance of happening in a given year at a given location. 100-year storm, 1 in 100 chance. The important thing to just keep in mind for our purposes is that 100-year storms are worse than 10-year storms, but they don't happen as often. Okay. And here we're looking at the number of these storms that are taking place or that have taken place over the eastern United States, both 10 years 10-year storms or storms that exceed the 10-year level and then storms that exceed the 100-year level. And they're both going up. They're going up statistically significantly. And if you look, you'll see at these percentage increases that actually the 100-year storms seem to be happening, or the rate of increase is faster than for the 10-year storms. So that, again, is a regional to national perspective, but there are also local factors that are important as well. So this is a paper from my PhD work. There in the middle, that gray blob is Charlotte, North Carolina. You can find similar results for other cities, but basically this is looking at summertime rainfall, both the total summertime rainfall and in the number of days with greater than an inch of rainfall. And you see a local peak in rainfall activity around the city. I'm going to come back to that with a more Wisconsin sort of example later on in the talk. Now I'm going to shift gears, though, to another Wisconsin example, actually the Madison example of what happened on August 20th. And so this picture here, first of all, actually I'm supposed to do it on the screen, so there we go. So, we have the outline of the Yahara watershed upstream of Lake Monona, so any rain that falls within this black boundary is going to make its way into the lakes. And then we have, let's see, all these dots around here. And what these are citizen-operated rain gauges. And so these are basically weather enthusiasts. They have these sitting in their backyards, and every morning they take a look and see how much rain is in there. And then there's a web interface to report that. If any of you in the audience do this, thank you. It's incredibly helpful. What we're able to use that information for is to basically validate and correct weather radar observations. So the same sort of stuff that you see on the Weather Channel, that's shown in blue there, but weather radar on its own is not very accurate. And so what we can do is we can compare the weather radar against those observations from the rain gauges, and we can adjust it up or down. And so then at the end of the day, we have a really nice picture, spatially complete picture over a large area of what happened. And when you do that, you pick up some really isolated, intense pockets like right there and right there of rainfall that was upwards of about 15 inches. Okay, so that's interesting. One thing that's worth noting here is that if you actually look at the rain that fell within the watershed, though, it's not a huge amount, in the sense that the storm was actually more to the west and southwest. And so one question that we had was, well, what could have happened here? And this shows if that storm had occurred 10 or 15 miles northeast, instead of getting about 4.5 inches of rainfall over the watershed, we would have been more like 8 inches. And so those of you who are around at that time can start to imagine what that would have been like. Not real great, I don't think. And so I mentioned that we do this work developing software. I'm not going to go into the details at all, but one of the pieces, or the main piece of software, is this rainy day. I've been really working on it since my PhD work. And what it allows us to do, among other things, is put together figures like this. And I'm going to just walk you through what's going on here. Basically, this is the probability of different amounts of rainfall affecting the Yahara watershed. And so 4.5 inches, what we actually got, is here, and that works out to about a 20-year storm. So that's, rare, but certainly not unheard of, and definitely within the realm of the sorts of things that engineers and city planners would be worried about happening. And then, on the other hand, if this more worst-case scenario where the storm had been a direct hit, that would have been more like a 200-year storm, or even more. And so if any of you are interested in more information about this, I do have an article in Wiscontext. I think there's a link to it on the Wednesday Night at the Lab webpage, and I talk about some of these issues in a little more detail. I'm not going to really say a lot more about, what to do about this issue going forward. We can talk about that in the Q&A if you like. But I will say a little bit about, why. So some people were calling the flooding like a 100-year flood. I just told you it was a 20-year storm. Where's the disconnect there? And generally speaking, those sorts of disconnects can happen for the following reasons. Really, the floods are recipes with multiple ingredients. Extreme rainfall is probably the most important one, but there's also things like land cover. So in urban areas, for example, if you pave over everything, where's that water going to go? And then other factors like soil moisture. So by that, what we're saying is, I guess the easiest way to think about this is, if you have a storm that hits and it's been raining for the past 2 weeks, it's going to be a lot worse than if it had been dry for the past 2 weeks, because the soil is not going to be able to soak up very much of that rainfall because the soil moisture is already very high. And then like any recipe, we have some additional spices. So depending on when and where you're looking, you might have snow involved, agricultural practices, high water levels of various kinds, and the complicated role of infrastructure as well. And so if you were trying to figure out what the recipe was on August 20th, I would say it's probably more or less this. But if you wanted to pick some other flood in some other place or some other time, the recipe would be different. Okay. All right, so that's, we're now shifting gears from talking mainly about precipitation to talking about floods themselves. And so, a lot of people, including climate scientists that I respect very highly, assume that floods are unequivocally getting worse because of the increases in heavy rainfall that we've seen. This paper that came out last year, it's a review of our sort of state of the understanding of this issue. You can see from the title there, if precipitation extremes are increasing, why aren't floods? So that seems to suggest that actually what we think must be happening maybe isn't happening. I'm going to argue a little bit against this over the course of a couple different examples here. But I want to just highlight one key thing, because as scientists, we're not allowed to just say whatever we think, or we shouldn't do that anyways. We're allowed to say whatever we want, I suppose. We have to have evidence for it. And so, I think that the authors of this paper would also say that, things might be happening, but we just don't have very good evidence for it. And I'll say a little bit about why that might be the case. So I'm going to show you a series of plots here that are showing typical data sets that flood researchers would be looking at to try to understand this problem of linkages between climate change and flooding. And so what we're looking at here, it says annual peak stream flow. And so what this really is in each year, what's the highest flow rate that river achieved? And so then, there are, I don't know how many years there are there, but there's one data point per year since about 1940 for this particular watershed, which is the Pecatonica River in southwestern part of the state in the driftless. And so what you see here are some pretty significant decreases in flood activity up to about 1980, and then things are pretty stable afterwards. And so what is going on there? It's basically improved farm management practices that have substantially decreased the amount of runoff that you get in response to heavy rainfall events. Okay? So there's that. This is another watershed. This is in Milwaukee. There might be, as I'll show you a bit later on in the talk, there might be a climate change component to what's going on here. But as I said before, land use is really, really important. This place has urbanized over that time period, and so really that urbanization is what's driving this sort of increase in flooding, and similar things can be found in other watersheds in Milwaukee as well. Okay, this is the Iowa River at Iowa City, and it might not be quite as obvious to you. What I see when I look at this is sort of one thing going on and then a drop, and then maybe something starting to happen there towards the end. And that's exactly what happened here. So upstream of Iowa City in about 1950, they started building the Coralville Dam specifically to control flooding in Iowa City. And it seems to have done that, although people living in Iowa City would say something seems to be changing there. And I think it's an open question, and climate is definitely one of the possibilities. Okay, and then the last one here is Turkey River, northeastern Iowa, actually not very far from the Pecatonica River. This is sort of a pet watershed where we do a lot of our work. It'll show up in some of the analyses later on as well. And here, what I see when I look at this is something that's more or less stable over time, and then towards recent, since maybe 1990, maybe the smaller floods are getting a bit smaller and the bigger floods are getting quite a bit bigger. And so, that might be, and I'm going to show you later on that we actually do think indeed this is an example of climate change. But taken together, then you can start to maybe appreciate the difficulty of parsing out that connection between climate change and floods, because you have to end up controlling for all of those other factors. And if you look at watersheds across the country and around the world, essentially, let me back up here, essentially all of them are going to be affected by some of these other factors. And so how do you know what is what? Well, I'm going to show you two examples where we actually try to step away, at least to a degree, not completely, but to a degree from using observations, and instead try to get at this problem using computer simulations. And one of those examples is indeed for this Turkey River, and then the other is for Milwaukee. Okay, so this is Turkey River. You can see it there in the northeastern part of the state. This is very much an agricultural watershed. There's really no urban land use to speak of here, other than a few small towns here and there. And again, this is another view of that same time series of annual maximum flood observations that we saw a few slides back. So, you see, as we said before, there seems to be this kind of stable behavior over time until about 1990, and then things seem to change with some low floods and some really big floods. And so this gray line, though, is the result, it's what we call a trend line. It's the result of a statistical analysis. And if you look at that line, it's just about flat. And so what you would conclude from that is, well, floods aren't even changing in Turkey River, let alone changing due to something like climate impacts. Okay, so that's sort of typical procedure. You could do this. You could get a lot of these sites. You could look at them and run this analysis and see what you find. We did something a little bit different, where one of my PhD students, Guo, who's in the back of the room, said, well, let's actually take these data and classify them just by when during the year they occurred. And so we've got in blue those floods in March and April, and in red those floods in May through September. And what happens when you do that is that idea of there not being any change taking place completely disappears, and you have two statistically significant results that, to some degree may be at the annual scale sort of canceling each other out. But, this is an example of how our typical ways of thinking about running these statistical analyses can lead us to very incorrect conclusions about what's happening. Okay, so what is happening? So as these trend lines say, springtime floods in Turkey River, they're decreasing in magnitude while the summertime floods are increasing, and that's really important because in Iowa and other places, the summertime floods are the ones that typically are very, very large, although I suppose this spring in western Iowa is a bit of a counterexample to that. Okay, so that is some interesting results based just on observations. But we wanted to attack this from a bit different standpoint here, and I'm not going to go through the details of how this all works, but I'll say what we're trying to do is basically, instead of just being stuck with the 70 odd years of flood observations that we have in Turkey River, wouldn't it be nice if we could have 10,000 or 100,000 years? I think that would be great, so let's see if we can figure out how to do it. The way that we do it is we start with this rainy day software that I mentioned earlier, and what that can do for us, we saw one example of what it can do earlier on in the talk, but another thing is that it can be used to generate really large numbers of hypothetical rainstorms. And then what we can do is we can put those hypothetical rainstorms in together with combinations of these other ingredients that you need to produce floods, and then run a really large number of computer simulations and then analyze what comes out the other side. Don't try this at home. We don't try this at home. We try this on very powerful computers. So originally doing this on NASA's Center for Climate Simulation system. Now we use this Center for High Throughput Computing at UW-Madison, which is a pretty unique system. Well, was unique, developed here at UW-Madison. Now it's used across the entire world. Basically, what it allows us to do is things like if a computer lab in this building or other buildings across campus, or if those computers are not in use, if it's in the middle of the night, for example, we can actually push our analyses to those computers and then wake up in the morning and get our results. So it's really nice to have a full night's sleep and feel like you're getting something done as well. And then we have a number of other of our own servers mainly for data storage and some computer processing as well. So that's a big part of what we do is worry about how to deal with these complicated computer systems. I'm going to show you what one of these flood simulations looks like. So what you're going to see, so this is the watershed here. You can see the river network. It doesn't turn out so well, but this sort of dendritic network here. And then this is the rainstorm, and you're going to see it move, and you're going to see the flood that results from it moving its way down that river system. So there, the storm is past, but the flood is making its way down. And so that's basically just a graphical representation of what our computer models are doing. And so you don't have to worry too much about the details here. I'm going to just give you the key points, but this is showing the results of, how many simulations is this?
10,000.
10,000, okay. And each of these 10,000 hypothetical events, we have the amount of rainfall that fell, we have the flood magnitude that resulted. It's a little hard to tell, but the dot sizes here correspond to how much soil moisture is present. Blue dots have snow involved in some way or another. So we can look at all sorts of different things, and we can look at that for past conditions, we can look at it for present conditions, and what we end up finding is that fewer floods these days are being caused by this combination of moderate rainfall on top of snow, so fewer of these springtime floods, more being caused by high soil moisture plus extreme rainfall in the summertime. And then I think what the most important point is, at least for engineers and planners, is that what used to be the 100-year flood in Turkey River is now about a 20-year flood, meaning it's happening about 5 times as often as we expected it to, and 5 times as often as all the infrastructure that's in place is supposed to be able to withstand. Okay, so that's Turkey River. Let's go to a bit more urban example. So this is another paper from my PhD work. This gray blob here is Milwaukee, and we're going to focus just very briefly on Cedar Creek, which is north of Milwaukee, relatively unurbanized, and then Menominee River, which is much more heavily urbanized. And if you take those annual flood records like we've shown for other sites, here we've broken them apart by 2 time periods, an early period and a late period. And the basic story is that in the early period, these 2 watersheds were behaving not exactly the same, but roughly similarly in terms of when in the year the floods were happening. But now there's been a complete turnaround in the Menominee River, and you see almost all of the flood events are taking place in the summertime. And so my colleague Long Yang, when he saw this, he really wanted to understand what the explanation was. And so, here's another point that's an important piece of this. So this is, again, sticking in the realm of observations. So on this side, we've got radar rainfall measurements, and here we have cloud-to-ground lightning observations. And so in both of those, you see just a bullseye of heavy thunderstorm activity right over Milwaukee as compared to the surrounding areas. And so Long was like, well, that cannot be purely coincidence. It doesn't make any sense that it would be. And so he did a really interesting set of simulations only for the July 2010 storm, which some of you may remember, that was a pretty bad one in Milwaukee. And what he did was, the 2 simulations that we're going to focus on anyways are what we call the control simulation, which is the real world, and then what we're calling the no urban simulation, where basically he's taken the urban land cover here, this red and pink, and replaced it just by cropland. And in this case, we're not using one of these flood simulation models like I showed you for Turkey River. What we're using instead is this thing that's called the Weather Research and Forecasting Model. So this is actually simulating how the atmosphere is working. And so instead of rainfall being an input to the model, it's actually simulating rainfall within the model. And so when he ran these simulations, he got the following result. So if you pull the city out of the simulation, so you have that no urban simulation, the amount or the peak rainfall for that 2010 storm goes down by more than 50%. Okay, so that's interesting. Certainly the urban area seems to be playing some important role here. And so urban heat island is part of it, but it's not the full story. So I'm going to explain to you what's going on here, at least for 2010, and we suspect this is going on more generally as well. So this is, again, an overhead view of the region. But what we're going to do is we're going to sort of turn this into a side view in a second and look along this A to B transect. And that's the transect. So there, we have the city, then to the east we have the lake, or in the no urban simulation we have farmland and then the lake. Okay, so I'm going to walk you through what happens here. So the July 2010 storm, like other storms in this region, most other storms, moved from the west to the east. Okay, so it's moving across Wisconsin. It reaches Milwaukee. Milwaukee's warm because of this urban heat island effect. What does warm air do? It rises. Okay, when warm air rises, the water that's held in that air is going to condense and fall out as rain because as the air cools, as it rises, it can't hold as much water vapor. That's how most heavy rainfall occurs. Okay, so that's something that we've understood pretty well in different cities around the country and around the world. But what happens in Milwaukee is a little more complicated. So what happens when that storm reaches the city, the air rises, you have rain falling. Well, as that air rises, some air has to come and fill in that void down near the ground surface. And the only air that's there is air that's over the lake. And it's holding a lot of water vapor because it's right over that lake and it's the middle of July. And so what ends up happening is you have the storm coming in, warm air rising, moisture rushing in, it's rising, producing more rainfall, also pulling more air in, and so there's this feedback loop that ends up making this rainfall much worse than it is in the no-urban simulation. And so what this figure is showing is actually the wind patterns along that transect. And you see, this is what we call a lake breeze intrusion, where the air off the lake is making its way all the way into the city, whereas here, that moist air from the lake isn't intruding at all. And so, that's just a single storm. A colleague and I have a proposal that's in review right now to hopefully have the chance to understand this a little bit better, and in particular to try to understand. So the Milwaukee Metropolitan Sewerage District, for example, has a very ambitious plan, actually the most ambitious plan in the entire country for increasing urban green spaces. And so can that greenification, I'm not sure that's a word, but can it help combat this sort of issue in Milwaukee, in addition to creating some nice spaces and having those trees to soak up some of that runoff as well? So fingers crossed on that particular thing. Okay, so that's basically the end of the talk. Just to summarize then, on the impact side, floods are becoming less deadly, but becoming much more damaging. I think this impact side needs a lot more attention than it has gotten historically. It's a really difficult thing to look at, and the paper that we just had accepted this week does start to look, at this sort of issue, essentially at a regional or national scale. How adequate is the infrastructure that we have in place compared to what we're facing these days? Recent increases in extreme rainfall. It's really, a combination of factors stemming all the way from global to local features. So, with the Milwaukee example being a clear case of that local effect. And then, despite what our observations say, so, I showed you that paper that said, well, floods don't seem to be increasing. I would say that despite what our observations say, that's actually not the case, because I, in fact, showed you two examples of how climate is impacting floods. But in order to really understand these sorts of problems, it requires really knowing the place where you're looking. So downloading all of the flood measurements from the whole country and just running some analysis, it's not going to work. You have to understand the specifics of what's going on. But what you do when you start looking at the specific circumstances in different places and you really understand what's going on, you see that, yes, the floods are changing due to climate. And so I'm going to stop there, and hopefully we've got some time for questions. So is this moderated at all, or do I just call on folks? Okay, sounds good. Yeah.
Could you define a flood?
Well, I guess it goes back to that distinction that I made. Oh, yes, sorry. So the question was, could you define a flood? It's a very good question, and one that's difficult to answer, I would say. So I made the distinction early on between flood impacts and floods as a sort of physical phenomena. So that is one distinction, right? when you say flood, do you mean the consequences, or do you mean the flood itself, I suppose? Even within the physical phenomena, though, you'll notice that I didn't say anything here about things like storm surge, sea level rise, that sort of business. I don't work at all on coastal flooding, and so I don't know very much about it, and I steered away from it intentionally. Although I will say that compared to sort of rainfall and river type flooding, the storm surge and sea level rise stuff is an existential problem because there's really no way to slow that sort of thing down. And so I'm not sure how that's going to play out. Does that sort of answer? No.
Is it water flowing over the bank of a river?
Sure. Okay. So that is a good definition of it. Yeah. So if essentially water is where it's not supposed to be, you could think of that as a flood. And so, there I was showing plenty of those plots that showed those annual flood peaks. Not all of those are events that have gone outside of the riverbanks.
So
Yeah.
to that point, don't you have to, or given the river, don't you have to consider the full capacity of that river over time? Whereas, there could be weeds growing, there could be outflow, runoff, dirt, and so the capacity of the river goes down.
Yeah.
So then the flooding will go up.
Yeah.
So the rainfall is not that big a factor, it's the capacity of that river over time.
Yeah. So the question here was, okay, well, rainfall is changing. There are these other ingredients, but what if the river channel itself is changing, and specifically if the ability of the river, or basically if the river channel is filling up with sediment or with weeds or something, that's going to play a role as well. That's absolutely true. And there's a fairly recent paper that kind of compared the importance of that sort of effect in terms of explaining changes that we've seen in floods versus the hydrologic effect, in other words, the rainfall and runoff and that sort of thing. And it's an important piece. It's not the most important piece, but that could be, so that's sort of at a national scale. In any particular location, it could be much more or less important. Yeah.
So I'm thinking that it might be an interesting exercise to go from Milwaukee to the globe, because quite a substantial fraction of the world's population lives in large coastal cities. And so the kinds of results we found for one storm in one city might apply on a global basis to a lot of the world's population over the entire year.
Yeah. So, excuse me, so the question was, okay, well, there are urban areas much larger than Milwaukee in other parts of the world, many of them in coastal areas, and so presumably that same sort of effect could be happening in other locations, and indeed it does. I don't know that literature as well as I probably should, but I've certainly seen stuff pointing to the similar sorts of behavior in Shanghai, and I'm guessing that there are other places as well. Everywhere is a little bit different, so we've done work in Baltimore, and there you do have some of the same stories, but there are complicating factors with the mountains to the west, and so everywhere is a little bit different, but in general, you're absolutely right. Yeah.
Since 100-year storms seem to be happening 5 times as often, are city planners now recalibrating what a 100-year storm is, or do they now just plan for 200-year storms?
I'm afraid to say that the answer is probably not either of the above. The question was, given that these types of storms and floods are happening more often, are planners and engineers really doing much about it? That was probably not a fair way to phrase it. It's not necessarily their fault. But in general, the answer is no, they're not doing very much about it. They're talking about it, which is the place to start. And so, for example, I had talked with some folks at the city engineering department about making some modifications to their stormwater management ordinance to increase, basically replace what they currently say is the 100-year flood or 100-year rainfall event, sorry, with a larger number. They ultimately decided not to do it, but did settle on some somewhat different sort of policy solutions to try to, at least for certain types of developments, increase the strictness of what has to be done in terms of controlling runoff. This problem is not going away, and I think this is going to start changing relatively quickly, actually. Between myself and a number of other researchers around the country, we have the tools now to provide answers, whereas 5 years ago we probably didn't. And so I think there's going to be increasing pressure to actually use those tools practically. Yeah.
Related to that question, that issue, where can we, citizens, find updated recurrence rates for these kind of extreme storms? Or
Yeah.
What's the answer? How can we help move our city planners and engineers in the right direction?
Yeah, so the question was, basically what can citizens do? Well, I guess there are two questions there. Right. Where can you find updated information? Right. And then, other things that you can do to sort of push people in one direction or another. In terms of updated information, I'm sorry to say that it's not so straightforward at the moment. So we have this rainy day software that I mentioned. We have a web-based interface for it. So you could certainly, if you wanted to, run an analysis for Madison or for anywhere that you like, really. So basically, you go to that web page. You can find it through my research group page, and you just have to enter a couple of things, and then you'll hit go, and it'll actually run on a server at the university, and then you'll get an email 15 minutes later with the results. The problem is that you kind of have to know what you're doing in order to get meaningful results out of it. So it's not quite as easy as I made it sound. It's easy to get results. It's also really easy to get bad results. Not that the software is wrong. There are particular things about how you use it that are important. In terms of the kind of advocacy part, I would say that you all probably know better than I do. First of all, just in the sense that I'm a newcomer in town, relatively speaking, and haven't been maybe as much of an advocate myself as I should be, although I'm not sure exactly what my role is in that regard anyways. I would say letters and whatnot, opinion pieces in newspapers and whatnot, it's never going to be a bad thing. Yeah.
Yes, could you comment in general about the relative contributions to these extreme storms of runoff versus the urban heat island effect?
Yeah, so the question was, what is the relative importance of this urban heat island issue versus, so you mean like the impacts of urbanization on runoff specifically?
More specifically, I'm familiar with what Madison is doing in terms of hydrological studies.
Yeah.
And I've had some conversations about some of the ordinance changes, but I've had very little luck in getting the city to take an interest in the urban heat island effect. And your lecture has been very stunning to me about the interplay in terms of water.
Yeah.
So I'm thinking Madison is different from Milwaukee because we don't have this large lake, but I'm just kind of interested in the general contribution of urban heat island effect in a city that doesn't have a large lake but still has an urban heat island effect. Somebody can't believe Madison has.
Yeah, we certainly do.
There's a lot of data on it.
There is, yeah. I'm afraid that there's not a clear-cut answer to that question at all. It's going to depend on the particular city. And even there, I don't know that we have enough data to really parse out, particularly when it comes to the extreme rainfall and flood side of things, how much across, a large population of storms or floods, for example, how much of that is really going to be due to heat island impacts versus other sorts of issues. So I don't have a good answer to it. I would say that, urban heat island we should be really worried about anyway, in terms of its impacts on vulnerable populations, not only of human beings, but incidentally of other sorts of animals that we're supposed to be trying to share our cities with, that really suffer from the heat as well. So I think it's something that should be really seriously thought about combating. And the way that we, in that Milwaukee work that we're hoping that we're going to be able to do is really framing this issue of the role of the urban heat island and heavy rainfall as kind of an add-on effect that we should be thinking about along with these other sorts of things when it comes to understanding the consequences of urban heat islands and the potential benefits of fighting them. Let's see if you had a question.
You made a really good point about the reluctance for the infrastructure changes to be made because they're expensive.
Mm-hmm.
What about the insurance industry? I'll bet they're reacting to it faster.
Okay. The question was, decision makers in this country are not seeming up to the task or willing to act on some of these things, but the insurance industry should be, presumably, if they have a stake in the game, right? Here's the deal. So when it comes to flood insurance in the United States, there's no private sector. Practically speaking, there's no private sector. There is a little bit, particularly for large industrial sites and things like that. But in residential properties and whatnot, it doesn't exist. And the reason for that is we have this national flood insurance program. It's very heavily subsidized. And so there's no way that a private insurer could compete. Now, I certainly talk with people from time to time in the insurance industry, and they have ideas for how they can try to break in, but from my limited time in the game, none of that has really gone anywhere yet. It's going to take a policy change for that to really happen. And if I'm being totally honest, I'm not a huge optimist about it. In other countries, the private flood insurance market is not very well developed either. It turns out that floods are really hard to insure against because they happen pretty often, they can be pretty devastating, and so the cost of a flood insurance premium, if it's not subsidized, is going to be quite high. And so that really leaves us in the place where, my opinion anyways, is that the main things that we should be doing about this are, first of all, certainly trying to do a better job of combating global climate change than we are. But in terms of more on the ground sorts of things, making sure our infrastructure is ready to handle what's coming, and trying to move people away from flood-prone areas. That last one being the most cost-effective one by far. Yeah.
Doesn't flood insurance kind of run against that idea of getting people to move away from flood-prone areas?
Yeah, so the question was, isn't flood insurance basically preventing that last possible effect of happening and moving people away? This is a big problem. FEMA does have programs in place where they try to deal with it to some degree of success. I don't know what degree of success exactly, but they do things like what they call buyouts. So if a particular property or even an entire neighborhood is being repeatedly damaged by floods, FEMA will just buy those houses and try to buy them at something close to not their market value, because their market value is very low, but something that they, roughly equivalent outside of a floodplain, and then those people could hopefully move somewhere else. So they do try to do this. I don't know exactly what that translates to in terms of the numbers of properties across the country that this is done with. Let's see. So I'll go with you, and then we'll go to the back.
So your study subjects, do you just decide you are interested in the Turkey River, or are organizations coming to you and asking for your analysis?
Yeah. Yeah, so the question was, why the Turkey River?
Well,
yeah. I would say it's a bit of both. It depends a little bit on exactly what research project you're working on. In the case of Turkey River, it really was kind of not random, but not very strategic either. I work a lot with colleagues at the University of Iowa, at the Iowa Flood Center there. And at some point, 5 years ago or more, I asked, hey, I need you to recommend me a watershed. And they said, why not Turkey River? I said, okay, let's do it. And so we've been sort of stuck with it from then on. And, when you're doing these scientific sorts of, let's say, more on the science than on the engineering side, you do have particular reasons for choosing one thing over another. Turkey River doesn't have urbanization, really, doesn't have any reservoirs. And so some of those sort of complicating factors are removed from the equation, whereas, if you look at this work in Milwaukee, well, the complicating factors are exactly what we're trying to wrestle with. And so it just depends on exactly what question it is that we're trying to get at.
But did the city of Milwaukee contact you, or did you contact them?
They didn't contact us. They basically, this proposal that we've submitted is through the Wisconsin Sea Grant program, which I'm not sure if folks are familiar with that, but it's a NOAA program, provides funding within the state of Wisconsin for coastal type work. And so what we did, we kind of dreamed up this idea, but then contacted Milwaukee Metropolitan Sewerage District and a few other groups within Milwaukee, pitched it to them, and they very quickly got on board with it. They were really excited about it, because they understand a lot of these problems. They know they exist, but they don't have hard numbers on them and would like to understand them better, don't have the resources or necessarily the expertise to look at them themselves. So, yeah, we had one in the back, yeah.
So two-part question. I heard that in a documentary that the sun's output fluctuates slightly on roughly 11-year cycles. The first part of the question is that true that affects precipitation, via increased moisture in the atmosphere? And part two, if so, do you have to factor that into your modeling, or is the effect so small compared to these other things that you can basically ignore it?
Yeah, so the question was, when it comes to climate change and its impacts on floods, are there sort of other things like cycles and solar activity? A climate scientist could do a little bit better job of answering this question than I can. But from what I understand, so first of all, those fluctuations are pretty easy to keep track of, right? And so they're certainly accounted for in climate models to the extent that they are regular and you can account for them, because these climate models, they take in you have to put solar radiation into them, and so if you know that solar radiation is varying on a regular pattern, you can account for it. And so once you do that, you can play games to understand, okay, how important is that are those solar fluctuations? And the result is that they're not very important. Some that have particular axes to grind would tell you otherwise, but if you actually look at the science, that's what people have come up with. Yeah. I'm not sure who was next. Why don't we just go here?
My question is about technology. Just last week I was studying the Willow Creek watershed, which roughly stretches from the Natatorian factor Whitney Way.
Yeah.
And there are really no good solutions. They've studied a lot. But in the process of looking at the discourse about this, I see the maps are just incredible. The maps of where the flooding's occurring, the map of where the rainfall is coming from. And 20 years ago, we didn't have anything like this.
Yeah.
And I'm wondering, how has your lab advanced the technology? How is this affecting the research that's happening? And I'm wondering, if you're in civil and environmental engineering, do you really need to be taking computer science, statistics, and math at the same time? Yeah, it seems like it's all computers.
Yeah. So the question was, how are the things that we do transforming due to technology? It's changing very, very quickly. On the stuff, I talked about being at NASA. So the idea that you could measure rainfall from satellites at the sort of relatively fine scales that you would need to understand things like floods, people thought that was crazy 20 years ago. And then 10 years ago, we could kind of do it. And then now we can do it with some reasonable degree of accuracy. And so who knows where it goes next. These floodplain maps, we can now measure land surface elevations with centimeter accuracy from airplanes using LiDAR, which has revolutionized this issue of generating these floodplain maps that FEMA needs, for example. So it's a huge deal. When it comes to education, it certainly presents a really big set of problems. I have two answers to this. One is we do certainly need to do a better job of integrating this kind of particularly computer programming and data analytics into our programs. The only way that we can really do that is through graduate education. There's not enough time to really get into the heart of that in an undergraduate degree program. And so college is too expensive already, I know, but the reality is that the sorts of challenges we're facing is true in other aspects of engineering and everything else. There's just not enough time in 4 years to cover all of it. And then, do we all need to be experts in statistics and mathematics? I don't think so. We need to know enough in order to be able to ask the right questions and find the right people. Yeah.
Couple more?
Sure.
When you're doing your project where you're looking at 10,000 years of climate, you're theorizing about most of that. How do you determine your accuracy?
Yeah, so the question was, if you're going to generate 10,000 years of hypothetical floods, how do you know you did the right thing? Carefully, I guess. No. So there are a couple things to keep in mind. One is we're not attempting to generate what the next 10,000 years looks like. We're generating 10,000 versions of what we think is going on right now, or in the recent past, or in some work that we're getting into at the moment into the not so distant future. And so that's where the observations still play a really important role. So I showed you in Turkey River, also in Milwaukee, how there are these sorts of seasonal changes that are taking place. There are also very much seasonal patterns in when precipitation tends to happen, when floods happen, when lower magnitude river flows are happening, soil moisture, snow, all these things we have a fair number of observations of, not as many as we'd like, but enough to make sure that we're credibly preserving things like these seasonal fluctuations and the variability from year to year in these different sorts of ingredients. And so once we've done that, we feel reasonably good about what we're doing. The other thing, this is sort of off into the weeds a little bit, but the specific way that we're generating these hypothetical storm events is directly based off of radar rainfall observations. So we are not inventing those out of thin air. Really what we do instead is say, well, a storm that actually occurred, somewhere else could have occurred here. And so we'll just take that observation and use it to understand what's going on here. So just as an example of this, the 2008 storm, that was bad here, but it was much worse in the Baraboo area. We include that in trying to understand what could potentially happen here as well, because it's not that far away. It's a reasonable sort of thing to think. And so we're not creating these things out of thin air. We're basing them as heavily as possible on what we really know.
Do you work with the DOT in developing models? I know the University of North Carolina has a big DOT department trying to predict what's going to happen in the next 100 years, so to speak. And they have a lot of data put together. They have a lot of stream information, highway flooding information, all that sort of thing goes together in these big models.
Yeah.
Do you work with these people about that sort of thing?
Yeah, so the question was the level of involvement we have with DOT, and it's a good question because flooding issues are really pretty closely tied to transportation issues and the infrastructure that goes into our transportation networks. We don't. So North Carolina is probably farther ahead than anybody else in the country on this sort of thing, with the possible exception of Iowa. In both of those cases, they've had really high levels of state funding support over multiple years, sort of free, well, relatively free of the vagaries of political change and whatnot. And so that's really what it takes to make progress on that front. So I certainly talk with the transportation folks in my department at the university, and I know they talk with people in the state DOT, but we just don't have the support to do it, I would say. And in fact, the way that the funding in Wisconsin DOT works seems specifically set up to prevent this from happening. And I'll just leave it at that. Do we have time for? All right, we'll just do one more in the back.
What about the Wisconsin Department of Emergency Management? Do you work with them?
I hear some chuckles. I'm not sure. So Department of Emergency Management, I don't know much about that organization, to be honest. There is a colleague of mine that's in the Space Science and Engineering Center, Shane Hubbard, he's a flood impacts guy, and his thing is working with municipalities and other agencies on emergency plans and also, basically long-term and short-term planning. And so I'm sure that he could do a much better job of answering that question. I haven't had any involvement with them.